Determination of salinity levels. Two cylindrical cans with insulating sides and conducting end caps are filled with water, attached to the circuitry shown in figure, and used to determine salinity levels. The cans are identical with radius r equals 5 centimeters and length L equals 3 centimeters. The battery supplies a potential of 10 volts, has a negligible internal resistance, and is connected in series with a resistor R equals 15 ohms. The left cylinder, this one, is filled with pure distilled water which has infinite resistivity. The right cylinder is filled with a salt water solution. It is known that the resistivity of the salt water solution is determined by the relationship ρ equals S0 over S in ohm meters, where S is the salinity in parts per thousand ppt and S0 is 6.3 ppt. Part A. The ammeter registers a current of 484 milliamps. What is the salinity of the salt water solution? So when I look at this, I see that here I have infinite resistance. Therefore, this is a capacitor that is fully charged. There is no current flowing through this capacitor. I have the resistance of the seawater, R sub S. I have the resistor with resistance R. There is no internal resistance of the battery, so we have epsilon here. And let's say that the current flows in this direction so that we have plus minus labeled this way. All right, so we're assuming that the capacitor is fully charged. So it is fully charged. Therefore, the current through the capacitor is 0. So this current that only flows through this branch is I multiplied by the equivalent resistance R plus RS. This must be equal to the EMF epsilon. So this tells us that RS, the resistance of the seawater, should be epsilon divided by I minus the resistance R. And here I have noted all the values given in the problem. You can see. And now, if I look at the resistance of the seawater, R sub S, it is the resistivity ρ multiplied by the length of the cylinder divided by the area pi r square. So remember that these are all cylinders with radius r, length L. Okay, so that is the resistance of the seawater. Now what is the resistivity? The resistivity was given as S0 over S, so it is S0 times L divided by S times pi r square. So S0 over S is the resistivity. And this we have shown to be equal to epsilon divided by I minus resistance R, which is epsilon minus IR divided by the current I. So with that, you can see S0L times I is S pi R squared times epsilon minus IR. So if I rewrite it here, S0Li must be equal to pi R squared epsilon minus IR times S. So this is basically pi r square S here multiplied with epsilon minus IR. So what does that tell me for S, the salinity level? So this gives me that S can be written as S0 Li divided by pi r squared epsilon minus I r. So it can be written this way. And knowing the current value here, we want to calculate what the salinity level of the seawater is. S is equal to, S0 is 6.3 ppt. So we're going to have 6.3 ppt for S0. The length is 3 centimeters. It's given here. It is 3 times 10 to minus 2 meters. So times 3 10 to minus 2. Then we have the current 484 milliamps, 484 times 10 to minus 3 amps, divided by pi r squared. What is the radius r? It is 5 centimeters. So it is pi 5 10 to minus 2 meters, parentheses squared, epsilon minus IR. Epsilon is 10 volts, minus I 484 times 10 to minus 3, R is 15 ohms. So calculating this expression, I find that the salinity level is 4.25 ppt, parts per thousand. That's the numerical answer to part A. Now part B says the left cylinder acts as a capacitor. Use C is equal to epsilon A over the area divided by the gap between the electrodes for its capacitance. How much charge is present on its upper plate? Note that pure seawater has a dielectric constant of 80 point, pure water, not pure seawater, pure water has a dielectric constant of 80.4. Okay, so now we're looking at the capacitance of the pure water. Capacitance is the dielectric constant, permittivity, epsilon, A area divided by the distance between the plates. The charge stored on it is the voltage appearing on the capacitor multiplied by the capacitance. And how much is the voltage that appears on this capacitor? It is I times Rs. So this is going to be I Rs times the capacitance C. So I will find that the charge stored on this capacitor is IRS. For C, I substitute epsilon A over D. IRS epsilon A over D. So this is the capital epsilon, capital letter epsilon, that's the EMF. The lowercase epsilon is for the dielectric constant. Okay, the relative permittivity multiplied by the permittivity of free space. So this gives me Q is equal to IRS, where epsilon is the dielectric constant kappa times permittivity of free space, pi r square is the area divided by the distance between the upper and the lower plates, and I finally obtain Q is equal to IRS is actually equal to epsilon minus IR. So you can see that here, epsilon minus IR is IRS. So I will substitute that for IRS, epsilon minus IR. Kappa, dielectric constant times permittivity of free space, pi r squared divided by the distance between the plates, d. So this is the charge stored on this capacitor. Now I can substitute the numbers. Q is equal to epsilon minus IR. So it is 10 minus 484 milliamps, 10 to minus 3 amps times 15, multiplied by the dielectric constant 80.4, permittivity of free space 8.854, 10 to minus 12, pi r square is pi 5 10 to minus 2 meters squared, divided by d, the separation between the plates. How much is the separation between the plates? It is L, which is 3 centimeters here. So this is 3 times 10 to minus 2 meters. So this gives me a total of 5.11 times 10 to minus 10 coulombs, which can be rewritten as Q is equal to 511 picocoulombs. Now looking at part C of the problem, at what rate is energy dissipated by the salt water? Okay, so that is part C. The energy dissipation rate is the power. It is the current flowing through the seawater, I square, multiplied with its resistance, Rs, which is I times IRS, which is epsilon minus IR. And that is 0.484 amps multiplied with 10 minus 0.484 times 15, I find that the power is 1.33 watts. That's the energy dissipation rate of the salt water. Now part D, for what salinity level would the 15 ohm resistor dissipate half the power supplied by the battery? Okay, so this is referring to a well-known theorem, the maximum power transmission theorem. So we note that when the resistance of the salt water is equal to R, and we have R in series with R, this gives us an equivalent resistance of 2R. So the power dissipated, it's going to be equal to epsilon square divided by 2R. V square over R, so it's epsilon square divided by 2R. This is actually the total power supplied by the battery. The power dissipated by the salt water alone will be, because the two resistances are the same, the voltage will be epsilon over 2 appearing on this resistor. Epsilon over 2 squared divided by R, it will be epsilon square over 4R, which is the power supplied by the battery divided by 2. So with that, when the resistance of the salt water, which is S0L, rho L over A, rho is S0 over S0 over S pi R square, S0 L over S pi R square is equal to R, this condition will be satisfied. Half the power will be dissipated by the salt water. So S will be equal to then S0L divided by pi r square resistance R. So for this salinity level, this condition will be satisfied. So if I substitute the numbers here, 6.3 ppt for S0, L is 0.03 meters, divided by pi 5 10 to minus 2 meters squared, resistance is 15 ohms, and that gives me a salinity level of 1.60 parts per thousand as the final answer to part D. Okay, so we're talking about determination of salinity levels. We have two cylindrical cans. One is filled with pure water, infinite resistance. This is just a capacitor. And because it has infinite resistance, that means there is no current flowing through it. It is fully charged. This has seawater in it. It's salt water, a saltwater solution. And it is known that the saltwater solution resistivity is determined by S0 over S, where S is the salinity level and S0 is 6.3 ppt. The dimensions are the same. R is the radius, L is the length, epsilon is the EMF provided by the battery, where the battery has no internal resistance. It's connected to resistor with resistance R. So first we know that the ammeter measures a certain current here, 484 milliamps. We want to know the salinity of the salt water. For that, we draw this circuit, equivalent circuit. We see that RS and R are in series connection here because there is no current flowing through this branch. And the current flows in this direction such that I times R plus RS is epsilon. So RS, the resistance, is epsilon over I minus R, but it's also equal to rho L over A, rho L over pi R square, where rho is given in terms of the salinity level as S0 over S. So this allows us to write S in terms of S0 Li, R, epsilon, and the resistance R. So substituting the given values, we can find the salinity level. In part B, the left cylinder acts as a capacitor. We can calculate its capacitance by using epsilon A over D. Epsilon is the relative permittivity multiplied by permittivity of free space, or dielectric constant multiplied by permittivity of free space. And the pure water dielectric constant is known. We want to know how much charge is stored. It's fully charged. It has the voltage multiplied by the capacitance equal to the charge stored. The voltage appearing on this capacitor is I times Rs. It's the same voltage across this resistor here. And I times Rs is equal to epsilon minus IR. So I can substitute that here. Kappa epsilon 0 is the permittivity, relative permittivity multiplied by permittivity of free space. Pi r squared divided by d, the separation between the plates. The separation between the plates is L. So that d is equal to actually L here. So instead of keeping it as d here, we should write L, because we note that d is equal to L. Okay, substituting the numbers, we obtain 511 picocoulombs. In part C, at what rate is energy dissipated by the salt water? It is the I square, current squared multiplied by resistance. I times Rs is epsilon minus IR, so it is I times epsilon minus IR. Substituting the values, we obtain 1.33 watts. For watt salinity level, the 15 ohm resistor dissipates half the power supplied by the battery. For equal sharing of power here, these two resistances should be equal. It's the maximum power transfer theorem. So this is a maximum power transfer theorem and here I show it explicitly. When the resistance of the salt water is equal to R, the power supplied by the battery is epsilon squared divided by 2R, the equivalent resistance. The power dissipated by R is epsilon over 2 parentheses squared over R. The voltage is shared equally by the two resistors. It is the power supplied divided by 2. So when Rs is equal to R, we can substitute for Rs S0L over S pi R square and multiply and calculate S from this expression as 1.60 parts per thousand.